Good evening everyone. Welcome to another episode. This evening it is space that we're going to take a look at. We're going to have a look at the various models of the solar system that have existed whilst we've been coming up with our ideas about the solar system and how they've changed over time and why they've changed over time. We're going to do the Nebular Model of Solar System creation, how you all got here, and then after we've established how our solar system was formed and our sun was formed, we're going to take another kick back about 10 billion years and we're going to talk about how the whole universe began. And if we've got time in 30 minutes, having established how the whole universe began and how you all got here, we might have a little bit of a chat about aliens, but that might be a tall order, so let's get started right now. So, back in the day when we didn't know too much about solar system physics, we looked up at the night sky and we saw stars and we saw random bright lights wandering about the place in the night sky, and we saw the moon. Okay, when we got some decent telescopes together, we started seeing that these wandering about stars weren't in fact stars at all, but they were kind of chunks of rock, and that they were planets flying around us. Now, you ask the average person what they're doing right now and they'll probably say they're sitting still. They are highly unlikely to tell you that they're hurtling around a giant fireball at 65,000 miles per hour, because that's just stupid. And that's where flat earthers and people like that come from, that it just doesn't feel right. So this was the old model of the solar system with the observations that were available at the time. We had this setup here, that we had the Earth sitting stationary at the center of the solar system. Now, for some people, it was actually the center of the universe, never mind the solar system, and everything in the solar system revolved around the Earth. And that makes sense. If you sit and watch the sun for long enough, it rises in the east, it sets in the west. You watch the moon long enough, it rises and it sets. You watch the planets as tiny little like bright lights in the sky. If you go outside in the evening time, you will see them. They're super bright stars. They are actually planets. You'll see them, and if you sit long enough, you'll watch them move across the sky as well. Though you may have to sit days upon days upon days to see anything vaguely that looks like motion. So that all implies that you're sat watching stuff go round, and that's okay, isn't it? So this is kind of your model, that the whole. By the way, check out the animations. Like it's just amazing. Okay, so the idea is that the whole galactic system is set up to go round the Earth, and that sat quite well with good old human beings and our feeling of entitlement and specialness, that we are special, that we were built and we were put here by some form of creator, and that the whole universe is our playground to have a bit of fun in, and obviously the Earth would be at the center. And we call this the Geocentric Model. Okay, geocentric. Geo kind of geography, that Earth kind of idea, and centric for the middle, so Earth middle model of the solar system. It sort of makes sense. And it's a pretty good model, actually. But there were some problems with it. Okay? And we need to discuss these problems, because this is how we ended up figuring out that we weren't in the middle. And most people that went to primary school know that the sun's at the middle of our solar system. But they just accepted that on faith. And that's not good enough, because at this stage we accepted on faith that the Earth was the middle, and we had some observation to back that up. So if you wanted to challenge this model, you needed some proof. You need some pretty good proof. Okay, so let's go proof. Proof one. Everything in the universe revolves around the Earth appears to be the kind of meme that's going on here. So when people looked at Jupiter, okay, eventually Copernicus, having a look through his telescope at Jupiter, started to see shadows moving across Jupiter's surface, and then later identified them as moons. You ended up with a bit of a problem, that if everything in the universe was going around the Earth, how could Jupiter have moons? How could things be going around Jupiter? Is Jupiter special? And then suddenly, what would it look like if you were on Jupiter? How would things look there? Because you would feel as if you were sitting stationary and these moons were going around you. And that starts to call into question your perspective on matters. This is a bit like being in a car traveling at 60 miles per hour. The only reason you know you're moving is because other stuff is moving around you. If I put you in a car at 60 miles per hour in a completely blackened environment with no form of signposts anywhere, and I cut out all the engine noise, you would have no clue that you were moving. So suddenly it became a question of, wait a minute, it might be that we're moving, we just don't know it. All right, so let's pop across to, so we've got Jupiter's got moons. Now let's have a little pop across to good old Mars here. Now Mars is good because you can see Mars in the night sky. And when you look at Mars in the night sky, Mars tends to just kind of wander its way across the night sky. So if I have like the horizon line here, then let's imagine that Mars is doing some form of little path. The path I'm about to draw is not the path that Mars takes, but you know, it's an idea. Okay, so it'll appear like any other night object, kind of come up, travel across, and drop down. Okay, kind of that way. And if you look at it over a period of time, it looks like it changes position as the year goes on, compared to the stars in the background. Okay, so if you're using them as your reference point, you know, it looks like it looks in different places. Now, that's grand. The only problem with that, and that's completely consistent with something going round the Earth, that's completely fine. The problem is it doesn't do that. The problem is that once every couple of years, it has a bit of a freak out, and it goes da, 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 and then goes whoa, and performs a loop for a few days. Now it goes on for a couple of years, and then there's another random loop. Okay, assuming that we're on a very long time frame here, and we've got this kind of backwards motion of Mars. And that's completely against everything we know about mechanics. Things that are floating around in free space don't just turn round. And they don't just turn around, perform a loop, and then continue doing what they're doing. And what's really happening here is that, now I'm going to need to up my ante in the old graphics department here. Let's imagine that we have Earth, and let's put Earth on this ring here, though it's not really on this ring. And let's put Mars on this ring. Right. Well, we know that the Earth, or at least we know now, the Earth is going around the Sun on a tighter path than Mars is, with a time period of about a year. Well, a year exactly. And Mars is going around with a time period that's much longer than that. And as a result, as Earth goes round, it overtakes Mars. It goes, all right, see you later, Mars. Flies around here, okay, which is fine. But at some point, it catches Mars again and overtakes it. And this is the loop, because imagine you're catching a car. Okay, imagine you're on a motorway and you're catching up with a car. Right, you're both going forwards, you both know you're going forwards, but you're catching them, you're catching them, you're catching them. Then as you draw side by side, you look exactly stationary to each other compared to like the background. And then, as you overtake, if you don't know you're moving, it suddenly looks like this one's going backwards. And that's a big deal, because that looks as if they were going one way forwards and then suddenly they reverse direction. But then as I get a little bit further forwards again, that kind of weird feeling of two things passing each other dissipates, and we get back to what kind of looks like we're all moving in the same direction again and everything's fine. Right. This is called retrograde motion, and is a pretty major problem with the geocentric model. So retrograde motion of Mars. And not just Mars, there are the other planets do this too, but Mars was probably most noticeable. Right. Happy? I hope we're happy on that one. So let's get rid of these and pop on a little bit further. So we've got moons on Jupiter, we've got retrograde motion of Mars, and then we've got the phases of the moon and other things. Now, if you look at the moon, what you're really seeing is kind of different parts of it lit up. Yes, you're not seeing the shadow of the Earth being cast on it or anything along those lines. You're seeing, if you're a slightly different angle, one side you're only seeing part of the moon lit up by the sun, and that's fine. But if the Earth was at the center, then every planet should exhibit broadly the same phases as each other, because the sun is just a ball of light wandering about the place. Right, so what we've got to do then is we've got to have a little think about what do we actually see, and what we see is the phases of the moon, which are grand, and then the phases of the planets that are further out from the Earth, or the further out as we know them now, have different phases to the planets that are further in from us. So your Mercuries and your Venuses have different phases to your Jupiters and your Saturns, and that shouldn't be the case if we were in the middle. So you kind of pile all this together. You've got moons, so we're not special in the middle. You've got Mars going backwards, which shouldn't happen and only happens if things are overtaking stuff. And you've got phases that suggest that we're not in the middle, that there's some form of weirdness going on with the sun and its position. You put all that together and you actually then get some decent proper telescopes, and you end up with a slightly different model. And the model we end up with is what we what we broadly work with now, which is called the heliocentric model of the solar system. Okay, so that is Helios, so helio for that. I think that's Greek for the sun, though I'm sure someone in the comments is going to correct me if I'm wrong on that. Centric for the center again. So the heliocentric model puts the sun at the center. And it's a little bit more complicated and required a lot more work, especially with the moon. We've got Mercury, Venus, Earth and Mars as the inner planets. And then we've got Jupiter, then you've got Saturn, Uranus and Neptune further out. Okay, you're dying for me to say Uranus there, I'll let you have that one, but I do tend to pronounce it Uranus. Further out. And of course you've got Pluto and you've got Kuiper Belt objects and you've got all sorts of things flying in here. You've got comets all around the show now. But broadly, this is what we've got at the minute. This is called the heliocentric model. And it differs from the geocentric model in a few ways. Like one, it has the sun in the center. Pretty majorly. It has the planets in completely different order. It has more planets on it, even though it's got rid of Pluto these days, tears. And it had to sort out this problem with the moon, that the moon goes around the Earth. But of course, I'm not showing all the moons. Like Mars has 2 moons of its own, called Deimos and Phobos. So like it's not like we're somehow special that we've got a moon. Jupiter's got moons, and Saturn's got moons coming out the wazoo. So moons are not a big thing. Okay, it just happened to be a bit of rock that's flying around that. Happy? Okay, so at 42 minutes, at 2042, we've got about 18 minutes left. So I'm going to leave that now, and we're going to go right. The big question is, we now accept this, though getting there was something of a problem. The Catholic Church, not a big fan of this model. Now, to be fair to the Catholic Church, they were the only game in town at the time. I'm pretty sure the Free Presbyterians would not have been a fan of this back in the day either, because it removes the Earth from its special significance in the centre of the universe and places a giant ball of exploding hydrogen gas in its place. So, yeah, that's a thing. Okay, Scorpion are Phobos and Deimos not apparently asteroids that are pretending to be moons? You end up in a problem there with how do you define a moon? Like it's something that's going around in a regular orbital pattern with a planet. Job done. Okay, so let's pop on. So if you're ever asked, by the way, who objected to this, it is the Catholic Church, and they do like Catholic Church because, see ya, sectarian. So moving on, we've got to go and see how we got here. So back in the day, about 4.5 billion years ago, kind of round about when your mom was around. That was a terrible joke. I'm sorry. I'll never do that again. I promise. We have a giant cloud that's lying about the place, and we're going to fill it in with a little bit of a gradient fill going on. Let's see if we can get the old gradient going on here. Everybody loves a gradient fill, don't they? All right. We've got a gradient fill of we've got gas here, lots and lots of gas. Now we need to know what type of gas, and the primary type of gas that's available in the universe is hydrogen, most common element in the whole universe. We'll talk about why a little bit later. So we've got hydrogen gas floating around, and along with that we have some dust. Now by dust we mean clumps of stuff. Okay, you've got bits of rock, bits of ash, bits of iron, all that stuff just lying around, hanging about in space, doing very, very little. Now, at some point in the distant past, there was an event. This cloud was just hanging out, being cool, doing its thing, when there was some form of shock wave went through it. Okay, something disturbed it from outside. And that was enough to start a process in place. Now, if I put a few dots in, okay, everything's kind of just floating about, doing its thing, but with a little bit of a jolt, a little bit of a judder, gravity takes over, and this is the primary force that runs most things in the universe. Gravity is very, very weak force. If you don't believe me, stand up. The entire planet Earth can't stop you from standing up. Your pathetic little leg muscles can do it. Okay, so little disturbance, but it's got an infinite range and it's always attractive. But like a mate of mine. But anyway, so what happens is, eventually this little particle gets attracted to this little particle, okay, because everything in the universe that has mass has gravity. The smaller you are, the more pathetic your gravity is, but it's not zero. And then when they stick together, they form a slightly bigger bit of dust. And that slightly bigger bit of dust has more gravity. So it starts sucking in all the stuff around it to make even bigger dust. and bigger and bigger and bigger and bigger and bigger dust gets bigger and bigger and bigger and bigger and bigger, eventually kind of migrates its way in towards the center and forms a large ball. Okay, and in this large ball we have a big pile of dust and gas floating around. Now a lot of it's gas because the vast majority of this cloud is gas. So we'll shade this in kind of orangey for no reason whatsoever. Now this has big enough gravity that it starts pulling things in at speed, and they start getting stuck onto it. Now because this is pulling it, oh, should have locked that in place, really, shouldn't I? Lock in place. Then as these things come flying in, the whole thing starts to spin. Like imagine you've got a big ball of rock with things coming flying at it at thousands and thousands and thousands of things coming bashing in and turning and turning and turning it round and round and round and round and round. Okay, so the whole thing is now spinning at extreme speeds. So let's get a spinny arrow in there. Let's go spinny. Right, the whole thing's spinning and it's getting smaller because all these little bits that are at the outside are now just coming in and coming in and coming in. So this whole thing is shrinking. I'm going to have to unlock that now. This whole thing is starting to shrink inwards, getting more and more dense as the stuff piles its way into the middle. Okay, so two things are going on here. One thing is we've got the collapse of the nebula, so it's collapsing in itself. It's spinning as well. So it's collapsing and spinning. Now, because it's spinning, that means that particles are rubbing against each other. And because things are rubbing against each other, we get friction. And everybody knows that if you rub your hands together, that causes friction, which generates heat. Now, normally when you have gases heated up, even the first years in here will know if you heat a set of particles up, they start to move away from each other, try to turn into a gas. But remember, you've now got the entire weight of the solar system coming in on you. Okay, all that gravity, like this little guy wants to get out. He's got all warmed up and he wants to fly out, but he comes out here and then he gets just sucked back in again because of the sheer gravity that's going on. So what you end up with is you end up with a disk that flattens out and ends up getting like spun round and round and round. Now, for my last pre-prepared graphic of the evening, you end up with this kind of thing going on. That you have this big bulbous ball in the middle, and spinning around like a record is the rest of the stuff that hasn't made its way into the center yet. And at this point, the world's or the solar system's biggest game of intergalactic pylon is going on here. Right at the center of this, there's a couple of little hydrogen atoms that are being crushed by the entire weight of the solar system. And that's too much for them to overcome. The temperature is at millions of degrees Celsius because of the friction going on. And those are the perfect conditions for nuclear fusion. So we've got, back it up here, we've got collapse, we've got spinning, that creates friction, that drives heat. And then we end up with massive pressure in the middle, which leads to nuclear fusion. Now I say that like it should matter, but nuclear fusion then is atomic bomb territory, right? In fact, hydrogen bomb territory, which is even bigger. So you get an explosion, but not just any explosion. Normal explosion goes bang. That's interesting. But this explosion, because it's inside a gravity well, it's contained by gravity, it goes bang and then gets sucked back in again. Okay, so it doesn't get out, which keeps some of the heat in, which makes it worse. It gets warmer again. So more hydrogens go bang, 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 bang. You get this kind of this runaway reaction where all this hydrogen starts to explode, one after the other, after the other, after the other, and the whole thing goes on fire. But it doesn't explode outwards like a big flame ball. It stays contained as a sphere because of all the gravity holding it in. And you've got a star. That's what a star is. You have pushing outwards all of this kind of explosive power going outwards, and we call that and I said power. Oh no, I'm Northern Irish, I can't say that word. But we have radiation pressure out. We call this radiation pressure. Basically, it's just the explosions that are going on, trying to push this whole thing outwards, but pushing inwards with equal force, or pulling inwards, I should say, not pushing inwards, pulling in with equal force, we have the gravity of the sun, which is why stars are big. They have to be big, otherwise it just goes bang and disappears. And that's it. I mean, not very interesting. It's just a very big bang, and or a very big explosion. We shouldn't say big bang in the context of space, but a very big explosion that goes outwards. And that's you. So, but some stuff does get out, or the stuff that didn't make it in gets blown away is probably a better way of putting it. That it was making its way in, and then this explosion happens and goes, oh, I'm out of here. And like most explosions, heavy stuff doesn't go as far as light stuff. So we end up in the situation where the heavy stuff ends up kind of near your newborn star. So if I put my new star here, okay, I'm just going to draw out here, you end up with rocks and stuff like that falling into little patterns here. Right? And they will eventually coalesce together and form your planets. Now they can't come together in their own little group and try and form like the provisional sun or something like that. They're going to end up they're stuck like this because of the gravity of the sun. It's stopping them doing that. The gravity of the sun is pulling them round in a circle because the gravity of the sun here is giving the centripetal force to keep all the planets spinning round and round and round, and thus stopping them from getting close enough together to form bigger objects. So we've got 4 inner planets, then we've got some leftover crap that nobody wanted, and this is called the asteroid belt. It can't form a planet because of this guy out here, which is the first of our gas planets, and that's Jupiter. Okay, and it's massive, and because of its gravity fighting with Mars's gravity, you can't get you're not going to get anything formed out of this asteroid belt. There is quite a large object in here called Ceres, but it's not planet worthy. Okay, we've got Jupiter next, then we've got Saturn further out. I should have made more of this diagram, and then on out past Saturn, we have Uranus, Neptune, and of course forgotten Pluto. Pluto being forgotten because it's a dwarf planet. There's piles of other objects out there, Haumea, Makemake, Sedna, that if you're going to call Pluto a planet, you have to call them a planet too, and making a rhyme up for that is disastrous. Okay, so that's us. That's us. Okay, so that's our solar system formation. Asteroid belt here is a worthy point. And how do we know this is right? What evidence do we have of this? Well, this is what we would predict. And then our observations back that up. Like we would predict an explosion would have heavy objects closer and gassy objects further away. And that's what we get. We would predict that if this was formed out of an explosion and then eventually came back together, that all these objects would orbit the same direction around the sun. And they do. We would have all sorts of reasons to believe that this is the way that our solar system formed. And of course, we can look at other nebulae, which is what a cloud of dust and gas is called, a nebula. We can look at other nebular systems in space and have a look at, because they're at slightly different stages in their progression. So this is the Nebular Model of Solar System creation, and is usually a 6-mark question on a SIA paper. Just describe the Nebular Model of Solar System creation. You're looking at 6 points here. So you want to wind this back afterwards. This is what you want. You want to start with nebula being a cloud of dust and gas. That's your first mark. Then that collapses and starts spinning. That then causes temperature to rise. When the temperature rises and the pressure gets big enough, you get fusion reactions occurring. That's your star being born. That's your 5 marks. And your 6th mark then is for the planets are formed out of the debris left over. Rocky planets closer, gas planets further away. Now we're running slightly shy on time. Hopefully we'll get through at least the Big Bang. We may not get to aliens in this one. We might have to ask if we can go a little bit over time. Right, Big Bang theory. So, where did this dust and gas come from? It's the obvious question, isn't it? There's a cloud of dust and gas. Where did that come from? Okay, so, where did that come from? It came from another star. Okay, a bit of a mic drop there and you can walk out, but that's not an answer. But it is true that any atom in space that is not hydrogen was at one stage in a star. So all the stuff in our solar system, the iron, the magnesium, the lithium, all those things were formed inside stars. Those stars died, their stuff went places, and then eventually it kind of ended up in our cloud and ended up with us. So you're literally made of stardust, which is awesome, but it doesn't answer the question, where did it all come from? So we have to take a look again at our night sky and work out what's going on. Right. Now, if you look at the stars from other galaxies, and I'm going to put galaxies on the screen because we are talking about galaxy level stars. That's collections of millions of stars. We're not looking at a particular star, but if we look at on a whole the stars of other galaxies, their light should be the same as the light from our star, okay, or at least stars similar to that. And it is and it isn't. That if you put it through a spectrograph, okay, which is a way of looking at really kind of detailed light, that you're not just going, oh, it's red, okay, you're going like, it's red of this wavelength, then you get this kind of pattern. It doesn't look anything like this, but you know, you get lines on a pattern like this. Okay, now if I take a look at a picture of a similar star from a distant galaxy, I end up with this. I get the exact same pattern. I'm going to deselect that, or that's not going to work, but it's slightly shifted. Okay, it's slightly moved this way. Okay, and if this end is the red end of the visible spectrum and this end is kind of the bluey violet end, then we call this redshift. Okay, the light is red shifted, and this is like the Doppler effect. It is a slightly different effect, but we'll go with that. It's like when an ambulance goes past you and it goes nee-no, nee-no, that kind of whir feeling. That this happens to waves as they move away. That they appear to be longer wavelength than they should be, and conversely, stuff that's moving towards you, it appears to be shorter wavelength than it should be. We call that blue shifted, but it turns out that our distant galaxies, the one are red shifted, that they're moving away from us. Okay, so galaxies are moving away from us. Okay, and that, you know, the kind of flat earthers again are having a great time with this, because they're going, well, if everything's moving away from us, then we're obviously at the center. We're not at the center. It's a bit like, imagine you're on a balloon that's being blown up, or if you're on any explosion, in fact, outwards. If you were at the center, that'd be great, but let's imagine that we were all kind of here. Now imagine you're on any dot. Pick a dot, not the center dot. Pick a dot, not the center dot. Right? And now I'm going to move them all outwards. Okay. It is true to say that now for your dot, you are further away from all the other dots than you were before. Okay, so if you're now completely further away, then you're not in the center, you're just one of another thing that's moving away. You could be at the center, or you could not be at the center, and you have no way of knowing whatsoever. Sorry. Okay, so that's not what this is about. Redshift is about explaining that galaxies that are further away from us, or that we see, are moving away, and all the galaxies are moving away. And worse, the further away they are, the faster they're moving away. So our universe is expanding. Now, the logic of that is, if our universe is expanding, right, then if it's this size now, 20 minutes ago it was smaller. An hour ago it was smaller. A year ago it was smaller. 4.5 billion years ago it was smaller. And we could do the calculation working out that eventually it would be so small that it would basically be an infinitesimally small dot. Okay, and we call this dot a singularity. And it appears to be the point at which all the energy, mass, time and space were crammed into a space smaller than a pinhead. Now, if you can get your head around that, you're wrong, because that's pretty much mind-breaking. But it's what the physics tells us, that at some point about 14.5 billion years ago, the universe was a dot, and that dot rapidly expanded. Okay, because having the whole universe in a dot is not exactly your most sustainable situation, so it expands rapidly outwards. Okay, in something akin to, but not the same as, an explosion. Like, you wouldn't call blowing up a balloon an explosion, but it's pretty good. Right? In fact, the Big Bang Theory was originally a term of mockery, that that this was presented as a scientific idea, and an objector in the crowd said, "Oh, so we're supposed to believe that the universe began with a Big Bang and it stuck." Okay, but yeah, you're meant to believe that the universe began with a Big Bang, and out of that Big Bang came all of our stuff. Okay, so 14.5 billion years ago, you have a singularity. That singularity expands rapidly, and this is what we need to know. Singularity expands rapidly. Okay, then we have the formation of protons and electrons. Okay, they kind of cool out of this. Right? They're naturally forming substances. Right? From that formation of protons and electrons, later we get hydrogen. When it cools down long enough for the proton to be able to capture an electron, you get hydrogen. And once you've got hydrogen and you've got it in enough quantities, you get hydrogen clouds. As the universe cools down even further, you get hydrogen clouds. Okay. And then once you've got hydrogen clouds, you've got a very basic nebula. You've got no dust in it, but you do have hydrogen, and you've got a nebula. And as a result of having a nebula, you can then go back to your nebular theory all the way back here, that the hydrogen attracts other hydrogen. Eventually you get a big ball of hydrogen that's rubbing together, collapsing, spinning, giving you friction, giving you heat, eventually giving you massive pressure, nuclear fusion, and an explosion that is the birth of a star. You get your first stars, and inside those stars are built your bigger atoms. Those stars die, they run out of fuel, they spread off into the space. That becomes part of other clouds, and you get that life cycle going on. And 14.5 billion years ago, it started. 4.5 billion years ago, roughly, our star got going, and we're here. And eventually, our star will die, and we will all be evaporated, and we will become part of different stars. So that's it. That's us. We're at 21:02 on the timer here, so we are out of time. So what I'll do is I'll maybe schedule another stream for doing alien life and kind of the end of the universe, because that's about a 20-minute topic in itself, and I don't want to keep you any longer. It's a half-hour deal on this one, so my apologies for not getting to alien life, but it's a big deal, and I want to have a proper rant about that one. So thank you so much for tuning in. Again, I appreciate, especially for my students who got off on study leave today, I really appreciate your commitment for coming into this one, and I will see you in the next one. And don't forget, everybody, physics rocks. It's true.